Video 8 covered context, meaning what the model can see and use during the current request. I'm Merdad, and today we're looking at the information that must survive after that context disappears. Here is the claim I want to establish immediately. A vector database provides storage, but memory is a system you run. Storage preserves information and returns similar text, while memory maintains useful state and recovers it when needed. That distinction changes how we design this entire component. The usual first move is embedding every message in a vector database, then searching by similarity on each new request. That approach gives the agent persistent storage, but it still doesn't create managed memory. Similarity can return whatever resembles the current query without knowing which fact remains true today. This embed everything reflex produces storage with a search box. Memory must survive across sessions while preserving state that changes, which requires more than saving and finding nearby text. Memory is a system you run, not simply a store you query. It first decides what deserves to persist, separating durable facts from temporary conversation and repeated phrasing. Then it consolidates related information and reconciles updates whenever old and new facts disagree. Finally, the system surfaces the information needed for the current decision, where similarity can support retrieval. Similarity cannot manage the whole lifecycle. The complete pattern is extract, consolidate, reconcile, and retrieve, with clear ownership, timing, and operating rules. This pipeline handles 4 jobs, although the slide groups them into 3 visual stages. Extraction runs on the live path, pulling durable facts from raw conversation while discarding noise. Consolidation then works in the background, where it merges duplicates, links entities, and reconciles facts that changed. Retrieval returns only the facts needed for the current step, then places them into the context window from video 8. Memory doesn't replace context, it supplies context selectively. By running these jobs on different schedules, the harness keeps the working window small, relevant, and affordable. Here is why embedding everything isn't enough. A vector dump ranks messages by semantic similarity, so it can find nearby language while missing the correct state. It loses event order, changing relationships and the distinction between an old fact and what is current now. Pure similarity also struggles when an answer depends on several causally connected steps. Managed memory changes the retrieval target by extracting and linking facts, then ranking them with relevance and recency together. Similarity tells you what looks nearby. Memory must return what is current, connected, and correct for this moment. Managed memory is also an efficiency mechanism because a small retrieved set costs far less than sending the whole transcript. The agent receives less context while retaining better recall, especially when questions depend on time or connected evidence. Mem0 reports its strongest improvements on temporal and multi-hop questions which require current state and several linked facts. The point isn't that Mem0 always wins. The useful lesson is where management helps, across changing state, elapsed time, and chains of evidence that simple storage cannot preserve. 2 ideas from operating systems make this design more concrete, starting with paging. Keep a small, fast-working set inside the context window, backed by a much larger memory store outside it. Page facts in when the task needs them, and page stale facts out when they stop helping. MemGPT applies this memory hierarchy to language models. The second idea is offline work, where consolidation, reconciliation, and cleanup happen while the agent is idle. Sleep time compute moves expensive housekeeping away from the live request path. The harness effectively wraps a fixed context window in a larger hierarchy, then performs maintenance when nobody is waiting. At production scale, this problem remains open because results from small, controlled benchmarks don't transfer automatically to real operational volume. As the store grows, many memories begin to look alike, and retrieval returns a close match instead of the exact one. EEAM makes that degradation visible as accuracy falls from millions to tens of millions of stored tokens. Temporal reasoning and multi-hop recall remain difficult at this scale, so don't assume memory quality stays constant. Measure degradation, preserve provenance, and create repair paths before the store becomes too large to inspect manually. This is the through line for the component. Memory is a background system the harness runs, not a lookup the model performs. Extraction, consolidation, reconciliation, and retrieval each need policies, schedules, monitoring, and clear ownership outside the model. The model uses whatever memories the harness places into context. The harness decides what persists, what changes, and what should return for each request. The model provides the intelligence, while the harness provides the machinery required to remember reliably. Here are the 3 takeaways. First, storage isn't memory because real memory extracts, consolidates, reconciles, and retrieves durable state. Second, borrow from operating systems by paging a small working set and moving consolidation outside the live path. Third, scale remains the frontier, since temporal and multi-hop recall degrade as similar memories accumulate. Design for that degradation before production traffic exposes it. Run the memory instead of merely querying the storage. If this series is useful, subscribe to Multi-Agent Academy, and you can also connect with me on LinkedIn. Next is Video 10, Tool Use and Routing, where we'll move beyond single-turn function calling. Multi-turn work is where the tool layer becomes the bottleneck. I'll see you there.